Hey there, future aviators. Welcome to Ground School. Go ahead and grab those notebooks, uncap your pens, and get comfortable. I'm your instructor for today's briefing, and my absolute promise to you is that by the end of this explainer, the magic of flight controls is going to be crystal clear. We're taking all that complex aerodynamics from your textbooks and turning it into practical, actionable knowledge that you'll actually use in the cockpit. All right, let's dive right in.
Okay, here's our flight plan for today. First, we'll cover the 3D axes of the airplane, followed by exactly how lift is created. Then we'll get into the primary controls, trim systems, and wrap things up with secondary controls.
Section 1. The 3D axes of the airplane. Let's start with the absolute foundation. Before you can control an airplane, you really have to understand the environment it lives in. Unlike a car that just turns left and right, an airplane operates in 3 dimensions. Quick note-taking alert here. You definitely want to jot this down. All of an airplane's movements pivot around one single, absolutely crucial point, the center of gravity. First, we have the longitudinal axis, an imaginary line running straight from the nose to the tail. The airplane rolls around this axis, kind of like a drill bit. Next up is the lateral axis, running from wingtip to wingtip. The airplane pitches up and down around this one, almost like a seesaw. And finally, the vertical axis runs straight up and down, right through the center. The airplane yaws left and right around this, just like a weather vane. Literally every control surface we're going to discuss today is designed to manipulate the plane around one of these 3 axes.
Section 2. How lift is created.
Now, before we start pushing and pulling levers, let me ask you, how does a heavy machine made of aluminum and steel actually stay up in the sky? Well, the answer lies in the anatomy of a wing, also known as an airfoil. Typically, wings have a relatively flat bottom and a curved top. As the wing moves forward, it meets the relative wind. Now, because air has viscosity, meaning it's slightly sticky, it tries to follow the curved shape of the wing in a smooth path called laminar airflow. Because the top is curved, the air speeds up, creating a low-pressure void right above the wing. Bernoulli's principle tells us that the higher pressure underneath will try to equalize, physically pushing the wing up into that void. Add in Newton's third law, where the wing forces massive amounts of air downwards as downwash, creating an equal and opposite reaction, and boom, you have lift. Note-taking alert number 2. Get this formula down. The lift formula. What's really fascinating about this equation is focusing on what you, as the pilot, can actually control. You obviously can't change the air density, that little rho symbol, and you can't magically change your wing surface area, S, in the middle of a cruise flight. But you directly control lift by adjusting 2 things, your calibrated airspeed, which is v squared, and your coefficient of lift, which is your angle of attack. Basically, if you slow down, you must pitch up, meaning you increase your angle of attack to maintain the exact same amount of lift.
Moving right along to Section 3. Everything about primary controls.
All right, so we know how the wing lifts the plane. Now it's time to look at the primary tools in the cockpit that you'll use to actually harness those forces. Let's start with ailerons. Ailerons control the roll around that longitudinal axis, from nose to tail. When you turn the yoke to the right aileron deflects upward, and the left aileron deflects downward. The wing with a downward aileron suddenly gets a greater angle of attack, meaning it creates more lift. The right wing creates less. This differential lift literally tips the airplane, causing it to roll right into a turn. But here is a massive warning, and you absolutely need to write this down in big, bold letters. Adverse yaw. When that outside wing's aileron goes down to lift the wing, it also creates a really nasty byproduct called induced drag. This drag acts just like an anchor on the outside wing, slowing it down. So as you try to bank left, the nose of the plane actually gets dragged to the right. How do we compensate? Well, it's the golden rule of flying. You must supply rudder pedal pressure in the direction of the turn to keep the nose coordinated.
Aircraft manufacturers know adverse yaw is a huge headache, so they've engineered some pretty clever fixes. First, consider differential ailerons, which are super common on Piper Arrows and Cessnas. The upward aileron simply travels further up than the downward one travels down, creating balancing parasite drag. Contrast that with freeze-type ailerons. When the aileron goes up, its leading edge dramatically dips down into the airflow under the wing. This purposefully creates massive parasite drag to perfectly counteract the induced drag on the other side. You definitely still need your rudder, but these designs make your job a whole lot easier.
Next up is pitch control on the lateral axis. Most planes use an elevator on the back of the horizontal stabilizer, but many aircraft, like the Piper Arrow, use a stabilator. With this design, there is no separate elevator. The entire horizontal tail surface moves. Because you're redirecting so much air, a stabilator is incredibly sensitive. To prevent you from accidentally over-controlling the plane and snapping the nose up, it features an anti-servo tab. This little tab moves in the same direction as the stabilator, but at an even sharper angle, creating aerodynamic resistance so the yoke actually feels heavy enough for you to control smoothly.
Section 4. Trim for relieving pilot fatigue. Now imagine holding a heavy yoke forward or backward for a 3-hour cross-country flight. Your arms would literally fall off. That brings us to the pilot's absolute best friend, trim systems. This is the secret to flying smoothly and professionally without exhausting yourself. The crucial thing to understand about the standard trim tab is that it acts like a mini control surface moving in the exact opposite direction of the elevator. If you want nose-up trim, the trim tab moves down. The airflow hits that downward tab and physically forces the main elevator up, holding it right in place for you. It's essentially aerodynamic power steering, allowing you to take your hands off the yoke completely in straight and level flight. Grab those pens again, write this sequence down, and memorize it for your entire flying career. Pitch, power, trim. First, establish your new pitch attitude with the yoke. Second, set your desired engine power. Third, and only then, adjust the trim wheel to relieve the pressure on your hands. Anytime you change your airspeed, power, or configuration, the aerodynamics change and you absolutely must retrim.
As a quick side note, while small trainers use those trailing edge trim tabs, larger commercial aircraft or certain distinct designs use an adjustable stabilizer. Instead of a tab pushing the elevator, an internal motor or hand crank uses a massive jack screw to actually pivot the entire horizontal stabilizer up and down. This achieves that exact same hands-off balancing effect.
Rounding out our primary controls is the rudder, which controls yaw around the vertical axis. You control this with your feet. Just like a wing, when the rudder deflects, it creates a sideward lift that swings the tail. Keep in mind the rudder's effectiveness heavily depends on airspeed and the propeller slipstream. The faster the air washing over it, the crisper the control. Also, some really unique planes use a V-tail, where two slanted surfaces, called ruddervators, combine both elevator and rudder functions to reduce overall drag.
Section 5. Secondary controls and high-lift devices. We are in the home stretch now. Gear up, because this final section focuses on secondary flight controls. These are the tools we use to physically manipulate the wing shape for the absolute most critical phases of flight, takeoff and landing. I want you to jot down the multitasking superpowers of wing flaps. Flaps are trailing edge devices that are absolute lifesavers. They increase the camber of the wing, giving you a massive boost in lift at low airspeeds. This delays your stall speed, allowing you to fly much slower safely. They also act like aerodynamic brakes by increasing parasite drag, which lets you point the nose down for better runway visibility without picking up excessive speed. Ultimately, they are the secret that allows us to land on short runways.
Let's look at how different flaps actually achieve this. The plain flap simply hinges down. It increases camber, giving great lift, but it moves the center of pressure back, which pushes the nose down. Now consider the split flap. This one drops only from the bottom surface of the wing. It provides slightly more lift than the plain flap, but creates massive turbulent interference drag behind it. It's fantastic for dropping out of the sky quickly without speeding up.
Now this next one is a favorite, especially if you're going to be flying Cessnas, the slotted flap. When this flap extends, it physically opens up a duct, or slot, between the wing and the flap. This brilliantly routes high-energy air from underneath the wing over the top of the flap, acting like an aerodynamic energy boost that glues the airflow to the surface. It delays airflow separation so effectively that it can lower your stall speed by up to 20%.
And for maximum performance, we have the Fowler flap. Instead of just hinging downward, the Fowler flap slides backward on metal tracks. This means it doesn't just increase the curvature of the wing, it physically increases the total surface area of the wing. During the first part of its extension, it provides a massive amount of lift with very little drag, making it incredibly efficient.
Moving to the front of the wing, we also have leading-edge devices. Fixed slots are permanent gaps that direct high-pressure air over the top of the wing to prevent stalling at high angles of attack. Movable slats do the exact same thing, but they deploy automatically. At high angles of attack, aerodynamic pressure pulls these slats forward to open the gap, keeping the air flowing smoothly over the top surface right when you need it most. Finally, we have spoilers. While flaps and slats create lift, spoilers are designed to entirely destroy it. They're large panels that pop up on top of the wing.
By instantly killing the lift, they force the full weight of the airplane firmly down onto the landing gear tires. This gives the wheel brakes maximum effectiveness so large airplanes can stop quickly on the runway.
And there you have it. You've just built a rock-solid foundation of how an airplane actually flies and exactly how you control it. From the invisible physics of Bernoulli and Newton, all the way down to the mechanics of ailerons, trim tabs, and Fowler flaps. Make sure you review those notes, visualize that pitch power trim sequence, and get ready. Because next time, you'll be taking the controls and feeling these incredible aerodynamic forces for yourself up in the air. See you on the flight line.